Hello, I'm Roberto, and we're going to present partial derivatives by theorem. One important theorem is the chain rule for partial derivatives. Another is the implicit function theorem, which is said when the functions are not given expressly. Lastly, the gradient theorem relates the gradient vector of the function to the external derivatives and helps. And we have an example. Suppose that if is defined on the stick D, that contains the point AB with the function f x y and f y x, and continues on this extent f x y a b equals f y x a b, and left the function to variables x and y in the partial derivative of f with respect to x is denoted by the f and is defined by, and here's I have the example and this.
Hello, my name is Jose Manuel Gonzalez Sanchez. I am going to explain an example about partial derivatives. Example: let chain be the function xif is equal x cubed minus y squared is plus minus 1. In this case, we have a function with a negative exponent on top. This lets us to decide to perform the derivative usando the chain rule, that is to apply the differential calculus from y is equal u at in, where u is a function and in is the exponent, is y is equal n multiply u for the n minus 1. So applying this to our function and first going to y with respect to the variable x, we have z is equal x to cube minus y to square is that minus 1. The shape is derivative partial z divided derivative partial x is equal minus parents x cubed minus y squared is this is all the minus 2 multiply 3 multiply for x for cube. Mm, Adjusting the partial derivative of z with respect to x is equal is minus 3 3x cube 3x squared divided in x cube minus y squared is the square. Now we must do the same thing with respect to the other variable y. If we look closely, we realize that the chain rule process remains the same, that only the factor that changes is the derivation of the function that has the exponent. The derivative partial z is derivative partial x is equal minus x cubed minus y squared. This is a minus square multiplied 4 minus 2y. Then the partial derivative of psi y respect to y is equal to is 2y divided in x for cube minus y squared sure all t cube because the result is equal derivative for c con respect to x is equal minus 2x squared divided in x cubed minus y squared equal the square y derivative partial of z respect y is equal to y divided in x squared x cubed minus y squared. This is on square. Also,
My name is Hector, and today I will talk to you a little about the partial derivative by the quotient rule and a small example. As you can see, the definitions indicate that if sig equal f x g, since to calculate if x, we consider theta is constant and we derive it with respect to x. Similarly to often by we consider that x is constant and we derive it with respect to g. Implement the use of the derivative theorems. The theorems to partial derivatives are the sum to were used for functions of a single variable which we will state as follows. Cf and g are functions to or more variables and c a constant. Then the following theorems are filled. Quotient rule. In calculus, the quotient rule is method of finding the derivative of a function that is quotient of two other function for which the derivative exists. The function to the f of the x can be written as f dx equal g dx and h dx. And h dx equal 0, the third rule states the derivative of gx hx is equal to the form. An example, the derivative of 4x minus 2 divided x squared plus 1 is the form equal x squared plus 1 times 4 minus 4x minus 2 times 2x divided x squared plus 1 um, square and equal is it comes down to this and result in tan equal minus 4 x squared plus 4 x plus 4 divided and x squared plus 1 and the square. The one below by the derivative of the one above minus the one above by the derivative of the one below on the one below a squirrel.
Let's do the partial derivative of this function. F of x comma y, x squared times y squared plus x plus y to the fourth plus 5, the constant 5. When we do a partial derivative, we only derivate the we only derivate with respect of one number, one variable, and we treat the other variable as if it was a variable, a constant. When you use a partial derivative, you might see this tree over here. These things means the same. We first gonna get the partial derivative of this function, this one function with respect of x. Then we have 2x y squared plus 1, because if we do the partial derivative of this thing over here, we have multiplication. We have x squared times y squared. When we have a multiplication, we use this over here, and the other thing we leave it like that. We have the derivative of x squared is 2x times y squared plus x, and the derivative of x equals 1. And this one over here, we treat it like they're constant. That's why we have these results of right here. And what we have now is to do the partial derivative of the function with respect of y, and is this thing over here. We have 2x squared times y squared. We have to derivative this thing over here with respect of y, and we have the derivative of y squared is 2y times this thing over here, and this is the same that I said. We have plus x, and as we are derivating with respect of y, we leave this one over here like a constant. Like a constant, and that's 0. Plus y to the fourth. We have to derive this y, and we have 4y cubed, and is this thing right here. And like this is constant, we leave it like 0, and that's all.